Hi, also, I mentioned that I was going to start making video keys for quizzes for my Organic Chemistry 2 class. I don't have a printed up copy of it, so I'm just going to start right now with the, just like the problems drawn out. So this was quiz 3. The first question was to draw the mechanism for this reaction. So this is electrophilic aromatic substitution, and the first thing that we really have to do is make the electrophile, because the thing that drives the reaction forward is the benzene going towards this electrophile. And so I imagine you would start this first. If you had your reaction, like if you're doing your reaction in like a flask or something, you would first add your aluminum trichloride or whatever your Lewis acid is with your whatever you need to make the reagent. And so the curved arrows for this is basically the electrons leave and go towards the chlorine, and then this chlorine attacks this aluminum, which is somewhat positive. There's a bond right here, but it's kind of hard to see. It's not positive. I guess it's lacking a full octet because aluminum only comes with three electrons, and each of these chlorines come with 7. So the total number of electrons for this Lewis structure is 24. 2, 4, 6, 8, 10, 12, 14, 16, 18. So 20, 22, 24. So you have 24 electrons spread around here. So your aluminum, even though it's not positively charged, is missing electrons. And the reason it's not positively charged is to calculate formal charge. You have the, you look at the valence electrons on the periodic table. It also corresponds to what row it's in. So aluminum is in row 13, so it has 3 valence electrons. And then it has 3 bonds around it, so it's neutral. So it's neutral, but it is missing a full octet. So it still has sort of an absence of electrons, even though it's not positive. And this chlorine is able to have sort of an excess of electrons, so it's going to move to attack. And then the structure you essentially get looks like this. Although there is technically a resonance structure that looks like this. So the positive charge moves up to be on the oxygen. I typically don't worry about that as much because the positive would rather be on the carbon than the oxygen anyway. So this really is the dominant structure, in my opinion. Other OChem teachers might argue with me about that, but that's how I feel anyway. So then we have our benzene. We would then add our benzene into our reaction vessel, and the benzene would attack at the positive charge because that's so positive that it's willing to make benzene break its aromaticity. So then this would add in right there, and we would get a positive charge right here. Because a new bond formed here. There's still a hydrogen. There's implied hydrogens all around these. So there is still a hydrogen here, but there's only one hydrogen here too. And so it only has 3 bonds, which is what makes this positive. So you can draw the resonance structures all around here if you want, but you don't have to. But then essentially the next step is the AlCl4, which was generated. This is kind of a bad habit of mine. I drew this, but I didn't also indicate that AlCl4 minus was a part of it. So that will come and take the hydrogen and leave the electrons in and restore aromaticity. And so you end up having basically substituted the hydrogen that was right here, the implied hydrogen, for this structure. So that is the mechanism. So that was the first question. The second question was, how would you get the following transformation? I believe it was, let me just double check. Yeah, so basically we're substituting this hydrogen out for a bromine. And for that you would need the halogen itself, and they only come in diatoms or diatomic molecules. So Br2 plus some kind of Lewis acid, and it's best if the halogen on that Lewis acid matches the halogen here. So FeBr3 or I think AlBr3 would be one. But make sure you have bromine here. I won't count off for the wrong Lewis acid. So these are the reagents you need to make this reaction happen. And then the very last question was, phenol is, I'll draw it and I will read it to you. Let's see. Can you see this on the page? Yes, excellent. Okay, the question says, phenol is an activated ring, meaning it is reactive and an ortho-para director. Using proper curved arrows, draw the resonance structures. There are 4 of the carbocation formed in the para addition of the nitronium ion shown below. Okay, so what that's saying is you're going to add, I think I just put NO2 plus just so you didn't have to worry about making the electrophile, but you're going to add nitronium and you're going to add it to the para position. Oh no, I actually changed this question. This question was supposed to be ortho position. So it adds to the ortho position. So basically it adds right here, right next to this. So nucleophile attacks and you get, oops, that goes away. Your double bond right there is gone. The double bond right here is what forms the bond with the nitro. And it formed at the ortho position. And then you have your OH here. So now where you bonded, there's a hydrogen there that's neutral. But then you get a carbocation on the other side of your bond, just like we talked about in the last video, or the last question. So this is what you end up with. A nitro added here and a positive charge right there. But because these lone pairs can come and fill in, there is a resonance structure that looks like this that adds some resonance stabilization to this molecule. So that is a resonance structure that I was talking about when I asked the question, draw the resonance structures. I guess there are 4 of them. So that's one that's really important. I think a lot of my students didn't get it, so I made this a bonus question. That's one resonance structure. So then I'm going to draw another one from here. Technically, you need to have this kind of curved arrow. If the benzene ring moved around, the double bond moved around the benzene ring, the positive charge would be here. Your nitro would still be here, and this bond didn't move. And then you could get another one where your electrons would move to fill in the positive charge. And so then your positive charge would be here, OH. And then you have a nitro here. So those are all of the resonance structures. 1, 2, 3, and 4 resonance structures that form, that show you how that positive charge on the aromatic ring is stabilized when you do addition. It also shows you why groups with lone pairs are typically ortho-para directing, because if it adds at the ortho position, that positive charge could be stabilized by the lone pair from the oxygen, forming a structure like this, or from anything else with an oxygen. So I just got a new camera and I keep forgetting I can zoom in for you. Look at that. So that's something I can work on. Anyway, okay, so that's the video key for quiz 3. Hopefully that was helpful to you. Let me know if you have any questions, and how do I zoom back out? Let's see. There we go. Let me know if you have any questions, and I will try to address them. Good luck studying!